Okay, so in this section we're going to do most of the vocab from 6-3, similar figures and scale drawings. Give you an idea what we're looking at here. On the left side, these are two figures. They're called similar because they're the same shape but different sizes. Notice one's smaller, one's bigger. And they're the exact same shape, and we'll talk about what that means too. We're also talking about scale drawings. These are things like map or models, things like that, that represent larger things in real life. And we're going to use fractions, proportions to help us solve them, which we've already learned. Okay, so we're going to start with similar figures. I'm going to draw two figures for you here. Two triangles. And I'm going to label them C, A, T, and D, O, G. And then I'm going to use this squiggle line. I'm going to say that triangle C, A, T is similar to triangle D, O, G. Now, I'm going to tell you right now the order matters on this. The order that I wrote the CAT and the DOG matters. Because the C, angle C, matches angle D. Angle C and angle D have the same measurement and similar figures. And I'm going to use these arc marks. You've seen these before, probably last year. Then I'm going to say that angle A matches angle O. Notice the order up top here. I'm going to use this order down here. So angle A, use the arc mark, matches angle O. Then finally, I'm going to say that the last one, T, matches G, and I'm going to use three arc marks. T matches G. And this is similarity. So it means they're the same shape but different size. In order to be similar, the first thing that has to be true has to be that their corresponding angles are equal. Okay, so we're going to type that in here for similar figures. Corresponding angles are equal. You know what? That's actually on the next two slides, so I guess we'll cover that there. Okay, so also the other thing with similar figures is the corresponding sides have to be proportional to each other. That means that if I were to try to form fractions, right? So if I were to give numbers to this, that if I said, oh, let's say this one's 10, right? CA. If you look at CA here, right? We see that DO matches CA. And look up here. CA matches DO. Look up top with me. CA matches DO. So if I said this one is 10, so CA is 10 and DO is 5, and then I said to you that AT is 8, right? And look up here, AT matches OG. What would you expect if AT is 8, what would you expect OG to be? So notice here, we said again, CA is 10, DO, or there's half of that, that's 5. So if this is 8, you might expect this to be, did you guess it? You would expect it to be 4, right? And if I said that this is over here, let's say 12, you might expect this one to be 6. So they're in the same ratio to each other. All the sides are. And on this one, it's exactly half, right? But on a different one, it might be a different fraction, different ratio. But this one, I picked something easy. So again, similar figures, corresponding angles. So angles in the same position are equal. They're exactly the same. And you can tell that by my little arc marks. And corresponding sides are proportional. In this case, I made them half, right, from one triangle to the next. Okay, so corresponding angles, those are the angles that are in the same positions on two shapes that are considered similar. So if I'm going to draw two rectangles, so I need to switch pens for that. I'm going to draw two rectangles, and like this. And I'm going to say that they're similar. I'm going to label these. We're going to call this one A, B, C, D, and this one W, X, Y, Z. And if I say to you that A, B, C, D is similar to W, X, Y, Z. Now remember, again, order matters here, right? So if I put an A here, that means that it matches the W. A matches W. Put the B here, right? And the X there. The B matches the X. And so on and so forth. So you go around the shape. Don't zigzag. Don't label it A, B, D, C because that doesn't make sense. You have to go around the shape. A, B, C, D. Again, this one, if you label it, don't go W, X, Z, Y. W, X, Y, Z. You have to go around the shape when you label it. So if they're in the same position here, oops, switch to the laser, same position here, right, that means that they are similar down here. So I would say that A matches W, those are corresponding angles, and B matches X. And C, now notice I'm putting the number of arc marks as I go, so 3 there, 3 here. And then finally D and Z match, so those are going to get 4 arc marks, 3, 4, 1, 2, 3, 4. So again, order matters. And these are called corresponding angles. They're in the same position. They correspond to each other. Now corresponding sides, so at similar figures, corresponding sides are proportional. And we talked about that a couple of slides ago when I gave you those two triangles, cat, dog, right? So we're going to do the same thing again here, and we're going to say C-A-T and D-O-G. Notice I went around the same order both times. And if I say to you triangle C-A-T is similar to triangle D-O-G, again, that means their corresponding sides are proportional. They're not equal because these aren't exactly the same triangles. They're proportional. So if, again, like I said, say this one is 10, right, and the matching side, DO, right, because CA matches DO, right, CA, DO. And I say this one's 5, and I say to you this one's 8, you would say, oh, then it's half, just like the other two are half, right? Oh, and then if I say that this one is 6, you could say this one is 3 then. So corresponding sides are proportional. I'm not going to make it always that easy, but that's pretty much the idea that we're looking at here. And the way to figure out the proportion, by the way, you take corresponding sides and put them over each other. So I would say CA, right, is like DO, right, because those two sides match up. I've got my laser here. CA matches DO. And I could turn that into a proportion. I could very easily say, fine, that's 10 to 5, right? It's a 5, which is really the same as 2 over 1, right? So 1 is double the other one. And notice that works really well. I can say AT and OG, right? AT matches OG, and, oh, that's the same thing. That's 6 over 3, which reduces to 2 over 1. So that is my proportion is 2 to 1 on this one, right? And you could use this to solve for one that you don't know. For instance, if I said to you, we know that CA matches DO, and I want to find, if I know CT, right, and that is going to match up with DG, now I just put in the numbers. So you could say, I'm going to switch here, you could say that I have 10 over 5, and that matches 8 over, well, I don't know, right, the unknown side, if I didn't actually give you the side already. And that's cross multiplication fun here, right? So we've got 10x equals 5 times 8 is 40, right? Divide off our 10, and x is 4, magically. So there you go, some more fraction fun included. Okay, so next we're going to talk about indirect measurement. This is actually one of my favorite topics. You know, I talk about the stupid stuff me and my sons do, like building trebuchets and other things. We actually use stuff like this when we're taking, like, say, a model and scaling it up, or a drawing, you know, and building a larger version of it kind of thing. So the great thing is, for indirect measurement, you can use indirect measurement to measure things that are too tall to maybe measure normally. For instance, I have a 5-foot person, they cast a 4-foot shadow. Notice this creates a triangle here, right? By the way, it creates similar triangles. As long as the things are standing near each other, because of the sun, like so the sun is up here, right? It's the red sun of Krypton, I don't know. Anyway, it creates, as long as they're standing next to each other, the shadows can be used for indirect measurement. So anyway, over here I have a 10-foot shadow from this tree. I don't know how tall the tree is. So I can use that to calculate it. So the way that really looks here, and again, we'll do lots of examples. This is just for your notes. You can say the bottom, right, 4, right, matches up with the 10, the shadow over here. And then you can say the height of the person, the 5, matches up with the height of the tree, and I don't know what that is. So a little cross multiplication fun, right? 4x equals 50, right? And then go ahead and divide off your 4, and x is 12.5, and I guess that's feet in this case. So that's what it's really for, indirect measurement. Now, we can also use scale in this case. This works with like models or maps, especially maps, because your map can't be the same size as the actual thing. It would be impractical. So I want a map of the city, right? It couldn't be as large as the actual city because you couldn't unfold it and use it. So it's going to be smaller. It's going to use a scale. So my example you can see here, right? You have to know what the scale is. Like for instance, you might say 1 inch, right? Hang on. Let's. I didn't want the line. Didn't want the line under there. There we go. So 1 inch. There we go. 1 inch might equal something like 25 miles, right? So you need to know that in order to make it useful. So an inch on the map, right, is 25 miles in real life is the idea. But an enlarged or reduced drawing that is similar to an object or place. So a map's a really good one. So, and I kind of mentioned this in the last slide, scale factor. It's the number that describes the size change from an original figure to its image. It can be a whole number or a fraction. So here, 1 inch on the map is 44 miles in real life. And this gives you an example of what we're going to do with it. So you can say map over actual, right? Map over actual. So 1 inch on the map is 44 miles in real life. That means 1.5 inches on the map is, well, I don't know yet, right? So they have to match up straight across from each other. And you cross multiply, right? 1 times d is d. 44 times 1.5 is 66. So we find that d is 66. So in other words, if I were to measure on that same map, if 1 inch is 44 miles, 1.5 inches is actually 66 miles. Don't forget your labels. Looks like they forgot their label there, right? So there you go.